section of the material for test 3, and then we will start reviewing. I would like to review whatever you need me to review for this upcoming test on Sunday. So the last section for the following test is 4.8, which deals with Newton's method. So let's talk about what it means and how he developed it and how he taught us to solve any possible equation, even the ones that we don't have an algebraic method to. So here is the scenario. Here's a function f of x, which obviously has a solution right here, a 0. So the equation f of x equals 0 has a root or a solution or an x-intercept for the function at r. Let's suppose that I use the intermediate value theorem to determine an interval where the function crosses the x-axis. So by the IVT, I will say number 1, function continuous on the interval a comma b. Number 2, f of a in my example is negative. F of b in my example is positive. Therefore, there exists by IVT. There exists. We denoted it then by C. Let's denote it by R because that's what they use now. It doesn't matter. You can use it. You can use any notation you like, such that f of R is 0. So this is not Newton's method. This is just telling us, giving us a 1-unit interval. This is not between 5 and 1500. This is either between 1 and 2, or 2 and 3, or 3 and 4. So 1-unit interval. Having that, we will choose to start the method at an initial value. So x0, initial value. We pick this. We should either pick A or B. It doesn't matter. So we should pick either A or B. Let's assume we pick B. For B, I will draw a vertical line at B. I determine a point denoted by P. The coordinates of point P, so let's say this is my x0, the initial value. I started at B. So the coordinates of P will be x0 comma f of x0. That's not a question. That's guaranteed. And let's suppose now I decide to draw a tangent at P. I extend the tangent, and it crosses, or it touches if you want, that's enough. It crosses the x-axis at this point. I'm going to say that this point has, I'm going to call it Q, let's say, and has the x-coordinate x1, and the y-coordinate, of course, 0. I can determine the slope of the tangent line in 2 different ways. One way is y2 minus y1 over x2 minus x1. F of x0 minus 0 over x2 minus x1, which is x0 minus x1. But I can also determine the slope of the tangent line at P by simply writing f prime of x0. The derivative at this point, evaluated, the derivative evaluated at this point will give us the slope of the tangent line, as we know from the previous chapters. All I'm interested in is in this equation now, and I want to solve for, what do you think? What do you think I'm interested in solving this equation for? So the reason is this. If I start with x1, which is this far away from the solution, and I get now x1, which is this far away from the correct solution, obviously x1 is a much better approximation of the solution. It's still not good, but it's definitely better than this one that I started with. So, of course, I'm interested in solving for x1. I will swap these two in a proportion I can do that, especially when the denominator here is 1. So, and I get x0 minus x1 equals f of x0 minus 0, that's gone, f prime of x0. Let me erase that to make sure that it's clear. It's not clear now. Sorry. So x0. So in order to solve for x1, I will move x0. And multiply by -1. Okay, now I'm here. I determined a better approximation than the one I started with. And at this point, I'm going to repeat the process, meaning I'm going to draw a vertical line. It crosses at point R. I'm going to draw a tangent line, which will hit the x-axis even closer. This will be, you can no longer see, it's so close. This will be at point x2 comma 0. And then I'll continue and continue and continue. Can anyone give us, without any calculations, what will x2, x up 2, equal to? Well, if x1 was dependent on the previous value, which was the initial value I picked, x2 has to be dependent on x1. So then x1 minus f of x1 over f prime of x1. What about x2? Will be dependent, x3 will be dependent on x2 minus f of x2 over f prime of x2. And so on and so forth. And this is Newton's method. And plus first iteration. So this was the initial value. This is the first iteration obtained after the first step. Second iteration obtained after the second step, and so on and so forth. And we can go on as long as we want. Of course, it's the previous one. If this is 3, this is 2. If this is n plus 1, this must be n. And everything the same in the function and its derivative. Now, there are two potential issues. One is do not start with x0 that makes f prime undefined, f prime 0. So f prime of x0 makes sure it's not 0. Because if you pick, let's say, 5, I pick 5 for x0. But if the derivative at 5 is 0, then the method will not give us anything. That is not applicable. The second potential issue is if I pick, which that's why we want to be as close as possible. So if I want to determine this solution and I start here, so there is a maximum between the actual solution I want to determine and my starting point, the method will never converge. I will only be here all the time. I will never get here. Well, this is very rare, but keep that in mind. that if you are starting somewhere and you're not getting anywhere, closer and closer, then there must be something wrong. Maybe the measurement unit, maybe you're using degrees instead of radians, or who knows what else. But it may be the case that you picked a point that is too far, and there is a max or a min between the initial value and what you are looking for. Okay, so let's see how this works. And you can now create any equation or give me any equation that you were not able to solve previously. If you have one, fine. If not, I will find one. Okay, so let's try this 17 if you don't have another. So 17 on page 342. And we have a 3 cosine x equals x plus 1. Well, no one can solve this equation algebraically. So our first step is to create a function. So we create a function. Which function? This function. This is our function, f of x. In step number 2, I have to say that the function is continuous as sum or difference of continuous functions, as sum difference of continuous functions. In step number 3, I have to find an interval where the function at one end is positive and the other one negative, or vice versa. In other words, I have to use the calculator, and in y equals, make sure the mode is in radian mode, and then in y equals, I have 3 cosine x and minus x minus 1. After I enter the function, go to second and calc. I'm sorry, second and table I meant to say. And just punch in some numbers. I'm going to start with, I don't know, -2, -1. I found a solution. There is a solution between -2 and -1. At -2 is negative and -1 is positive. So I will say between -2 and -1. At -2, the function is less than 0. And at -1, the function is greater than 0. I don't have to write what it is. It's not important. So now keep in mind we're trying to find a solution between these numbers. I will have to say number 4, by IVT, there must be a solution, and R in the open interval -2, -1, such that f of R is 0. In the next step, step number 5 if you'd like, I create Newton's method. I like to call it Newton, but what I'm really interested in, first of all, I have to pick x0, and I will create a function that I will put in the graphing calculator. So let's pick x0. It doesn't matter. You want to start at -2 or you want to start at -1. But we have to make sure that the derivative of this function is not 0 at the point you are picking. So when I plug in, let's say if I start at -2, this is not going to be 0, -2, so this is 2 minus 1, and this is not 0. You can check if you like. Right? We already know that. I'm sorry. I didn't create a derivative. I'm sorry. I have to find a derivative. I didn't. So f prime of x is -3 sine x and -1. So it doesn't matter what I pick at -1 radian. -1 radian is about 60 degrees, and this would be the square root of 3 over 2. This is not going to be a 0. So this would be positive, this would be negative. At negative 1, again, sign of negative, so negative 2 actually, you can check. Let's check. But absolutely not. I can start anywhere I want. So I'm just going to put the second function. I don't want to delete what I have. So negative 3 sine x, and then minus 1. And go to second in calc, second in table. And at negative 2 is 1.7, and negative 1 is 1.5. The function in red was a derivative. So we are safe. So now I want to create the function that I will be using to determine the solution. And that will be x minus the function at the top, 3 cosine x minus 1, the derivative in the denominator. Since both negatives, I'm going to factor and change this into positive. So this is 3 sine x plus 1. I don't want to have too many negatives. The final step before we put this in the graphing calculator, let's say we want 6 decimal digits accuracy. So we know when to stop. Next step. In y equals, you can delete the derivative, the second one, but do not delete the first one because I have to start with x. So insert, second and insert x, and then plus. Don't forget to put parentheses around the numerator. So I have x and plus parentheses for 3 cosine x minus 1 minus x minus 1. Close the parenthesis for the numerator. And divide by this, in parentheses, 3 sine x, close the parenthesis, and plus 1, and close the parenthesis. At this point, you need to second and quit. Clear, you don't need to do that. So let's go to variables. It's this key, variables. And then we go to y variables. Scroll to the right. And we call the function. Call the function. I'm calling function y1. And I decided to plug in. No one told me anything, so I'm going to plug in negative 1. So I start with negative 1. That's my starting point. You can start at negative 2. It doesn't matter. Okay, so I plug in negative 1. And when I plug in negative 1, what am I obtaining? I replaced x by negative 1 everywhere, 1, 2, 3 spots, and when I click enter, the answer I get is the first iteration, the first approximation of the actual solution, negative 2.0632999097. I copied everything I see. I could say, oops, I'm in danger, potentially, because this is outside of the interval. That's okay. It's okay. Now let's look at the second one. Here is how I do the second one. I copy second and the previous entry, because now in the function I have in the calculator, I want to plug in this number. So override negative 1 by second and the previous answer. And don't forget to delete anything else that is there. So I have y1 now that will be evaluated at the previous answer. And when I press enter, I know I'm on the right track. Negative 1.847169903. You can ask, why are you copying all these? In a moment you'll see. Now for x3, I don't have to do anything else, just copy the previous entry, and the function will be evaluated now at this point, and press enter. So I have negative 1.8623133932. I repeat as many times as I need. x4, the fourth iteration, is negative 1.86236499. And we said 6 decimal digits, 1, 2, 3, 4, 5, 6. They're not repeating, only 4 are repeating, so I have to go one more. So x5, negative 1.862364929, which is identical. So that's all I need. If I want to include this, because it's higher or I round up, it doesn't matter. So we found in 1, 2, 3, 4 iterations, 4 steps, we found a solution of the equation with basically 8 digits accuracy.